Good afternoon. So welcome back to my natural language processing class. So this is the second week, and we are going to discuss model and data. So before that, let's first take a review of the semester plan. As I showed you at the end of the previous lecture, right, there will be many weeks ahead. And I organized this in the following patterns. So for this week, I'm going to discuss the overall framework and lay some backgrounds. For example, I will discuss with you the correlation between model and data. Okay, how do they work? What are the common backgrounds you need to know before you build an NLP model mathematically? And then for the next few weeks, you will see a row of linear models. They are simple, but they are the foundation of more advanced models. For example, in week 3, the week after this week, we are going to learn simple counting-based algorithms. So for example, we will learn how to build simple language models by counting the number of words, right, in a large data set. And we will also learn a text classification model, okay? So you're given a piece of text, you classify whether this is positive sentiment or negative sentiment, right? Based on counting, right? So you count the number of words that co-occur with positive or negative sentiments, and you predict, okay, whether this text is positive or negative. So this kind of methods were developed in the 1980s. They were very ancient, but they provide a lot of necessary background. And then moving on to week 4, we will start to talk about representations. Okay, this is a very common term in NLP. We will see a very simple method how you can represent, okay, a document in a vector space. And then we will review a few models which you are familiar with, such as SVM. I think you learned that in your machine learning class, and perceptron. You learned that in your machine learning class, but I'm sure you will see that from a fresh perspective, okay, in NLP. So this one, okay, is called the generative model because they try to solve problems by generating things, okay? And this kind of feature-based models are called discriminative models because they try to make predictions by differentiating, okay, different kinds of outputs, okay? So, and then moving on, week after next, I'm going to show you that a lot of discriminative models, okay, they are all different instances of a general neuron, okay? So I'll build a connection between these feature-based discriminative models with deep neural networks by first telling you that, okay, they are just all different instances of the neuron. Okay, I'll tell you what is a neuron, and I'm going to tell you how to train a neuron using stochastic gradient descent, which is a basic optimization algorithm that are used still currently for training large language models. Okay, so so these are all text classification problems, okay, and language modeling problems. You have not known what is a language model, but I'll show you next week, and I'll give you a hint today, okay? And then we are going to talk about some information theory. What is entropy, what is perplexity, etc. So these are useful because they serve not only as a training objective, but they can also serve to evaluate models. Okay, they are closely related to language models, and of course large language models. And in that week, I will also talk about the representation of words. Okay, how do you turn words into a vector? And then week 7 is a little bit different from these 4 weeks because I'm going to show you, okay, how to build generative models, as I mentioned to you, okay, and discriminative models, as I mentioned to you, for structures, okay. I'm going to use like sequence labeling. I think you remember last week we talked about part of speech tagging, CCG super tagging, right? And maybe named entity recognition as an example. I'm going to show you how to build generative models and discriminative models for these structured tasks, okay? The thinkings are very similar, but because the problems are different, the models have some differences, right? And I think that's pretty much from 1980s to even 2010s, okay? But then the whole research field changed, you know, into neural networks. So from week 8 onwards, we're going to embark on the discussion of neural networks. So, and this week we are going to generalize, okay, not to generalize, but basically to extend the single layer perceptron into multi-layer perceptron, or MLP. So this is a foundation of building neural networks, okay? And we're going to extend the word representation here, okay, into neural word representation, okay? So you will see the difference between what people do for representation in the like linear model age and in the neural era. These are different. And we're also going to extend the language model we learned here and the text classification model we learned here into neural versions, okay, multi-layer perceptron versions. So week 8 is an intersection. So it serves to like switch from a traditional point of view to a neural point of view. And then provided that you have a multi-layer perceptron and you have word embeddings, like dense word representations, we can go on. Like moving to week 9, I'm going to introduce you a paradigm shift. Okay, so how do you use neural networks to represent whole sequences? Like a neural representation of full texts, okay, which serves as a basis for building both classification and structure prediction models. So you will see convolutional neural networks, recurrent neural networks, and also self-attention neural networks, etc. in this week. Maybe you're learning at the same time convolutional neural networks for computer vision, but in natural language processing, it's a little bit different. Okay. So this is a very important week. And then week 10, we're going to jump into structured prediction again. So week 9 is still text classification for the neural paradigm. And then week 10, we will see, well, if you use a neural model to solve a structured prediction task, then it's very different from when you use a traditional model to solve the same tasks. Okay? We will talk about a neural structured prediction in this week. And then, so this week we learned neural sequence representation, and this week, week 11, we will learn how to use a neural network to represent structures. Okay? Now that you can predict a tree, a graph, etc., so you want to use neural networks to represent them. Okay, find their representation. So graph neural network, tree LSTM, this kind of stuff. And then week 12, we will move on to something called sequence-to-sequence models. This is a very important foundational structure nowadays. Okay, so we will learn transformer as a very salient model in sequence-to-sequence. And we will also extend the language models we learned here and the language models we learned here into a more general language model, okay, recurrent neural language model, masked neural language model. So in this week, okay. So, and that provides us a foundation for a technology called pre-training, which is a foundation for large language models nowadays, okay. But in the field, like in between 2018 and 2022, I think, there was a period of 4 years where our field undergoes an era called pre-trained language modeling era. Okay, so basically, you can think about it as a smaller version of large language models nowadays. Okay, we will reveal those ages, and I will show you how these kind of language models are used to solve every NLP task. Okay, and then for 2 weeks, we will move on to large language models. I will tell you something called the scaling law. So when the size of the data, when the size of the model grows, well, you will see new capabilities emerge, okay? And a large language model, the term came out from here, from the scaling law. And then I will show you what kind of new tasks are solved in large language models, and how do you train and tune and use a large language model. And in the final week, I will give a brief review of the boundaries of NLP. So what can LLMs do nowadays? What can they not do? Okay. And I will also show you some like ethics and safety concerns of NLP and AI technology. Of course, I will also discuss AGI, artificial general intelligence, and ASI, artificial superintelligence. So that's a big picture, okay? I didn't have time to walk you through this big picture last week, but I show you now. Many of the things might seem unfamiliar to many of you. It doesn't matter, right? I will go through the details one by one. But I guess you should bear in mind this picture. So every week before you learn the class, and when you preview the class, you take a look at the picture and think about where you stand, okay? So for this week, we are going to discuss the basics. I'm going to review some concepts, and I'm going to discuss the overall framework. So there are a few goals. So the first goal is the overview of our modeling paradigm. This overview will not be repeated week after week. So I will assume that everyone will bear in mind this overall framework, okay, when you learn the other weeks. So when you see an equation, for example, in week 3 or week 4, you don't know where it fits, you review this week, okay? So that's the purpose. So we will lay some common background for the subsequent weeks, which I will not repeat, okay? And I will also discuss the role of data in NLP. I will show you several examples on how you curate the data, okay? What kind of things you need to take note of when you curate the data. And I will show you some linguistic details, okay? That might be the only week we touch upon a little bit linguistic details, okay? And finally, I will review the probability theory. So I think in your math class, you have learned a lot of probability theory. You've learned calculus. You've learned linear algebra. These are all very important, okay? But I will just review some probability theory, which are essential for this class. And the organization is going to be like 3 sections. The first section is going to be the modeling paradigm. So I will discuss with you the role of data and model in NLP. The second is about data curation. So let's go to some data processing, data crawling issues we need to know. And the third part is about probability. Okay, so let's roll up our sleeves and look at some basics. Okay. So the first part is about model and data. So here I draw you two pictures. Okay. So on the left is the test scenario. Okay. How do you use an NLP model? So, well, it's as simple as in this chart. You have an input, you feed the input to an NLP model, and the NLP model will give you an output. Okay? So that's the paradigm. So let's take machine translation for example. You have a machine translation model here, right? You have an English sentence here. And then you feed that to a model, it will generate a Chinese translation, right? So, so this is a scenario I guess most of you knows, but later if you find something out of context, you remind yourself of this scenario. And for training, the model, okay, is a machine learning model. As I mentioned last week, I'm going to discuss natural language processing in machine learning perspective. So you need to train the model before it can be used, okay? So how do you train the model? You have to collect a set of data, all right? And then according to the data, you train the model. The model will be ready for making predictions, right? So this is the two scenarios. Okay, testing and training. And of course, when you look at this picture and when you look at that picture, there are only two important things. One is data, right? The input, the output, okay, the data to train the model, and the other is the model, all right? So let's first review, okay, the data. Okay, what kind of data are we going to play with in this whole course? I categorize NLP tasks into three types. There are classification, structured prediction, and generation. Well, these are three very big categories, right? And I'll show you examples one by one. So here you see classification, right? Two different tasks. Sentiment classification. You remember? The input is a sentence, a text document, and the output is a label, right? Positive or negative or neutral. The second example is natural language inference. For this problem, there are two inputs, the premise and a hypothesis, a pair, right? And when you have this pair, the output is still one of a few labels, entailed, contradict, or neutral. All right? So the inputs are slightly different, but the output is one class out of a set, right? So this is called a classification problem. All right. The second is structured prediction. I have a few examples here to show you. The first is called part of speech tagging. You have a word sequence, right? A sentence. The cat sat on the mat, period. The output is another sequence. So each label in the output corresponds to a word in the input. So this is called sequence labeling, okay? I give each input token a part of speech. So to map the word sequence into a pulse sequence, okay, part of speech tagging, sequence labeling. There are other sequence labeling problems. And the second example is dependency parsing, okay? So the outputs are word-word relations in a sentence, and the input is a sentence. And these word-word relations, they form a tree. As you learned in discrete mathematics, a tree is a graph with n-1 edges and nodes, okay, and it's fully connected, all right? So that's a tree. So dependency parsing typically outputs a tree structure. All right. The third example is named entity recognition. So the input is a sentence. The output are a lot of spans out of the sentence. You chunk the sentence into spans, and some of the spans are named entities, and you label them. Other spans are not named entities, and you leave them. Okay, so this is, I would say, a part of sequence segmentation problem. Okay, so the last is relation extraction. So you identify the relations between entities you recognize in a sentence and build arcs and label the arcs. So, okay, no matter whether you're doing pause tagging or relation extraction, the outputs are a set of substructures that are intercorrelated with each other, right? So there are arcs, there are arc labels, and one arc might depend on another. There are part of speech here and there, and the part of speech, they depend on each other. The previous part of speech is a determiner, the next part of speech can be a noun. Okay, so it's called structured prediction. Okay, you output a structure. There can be structures that are even more complicated than simple tree or sequences. There could be joint tasks. Okay, I'll give you an example. If you're doing word segmentation, which is to chunk the sentence from character sequences into a word sequence, right? And then you want to perform part of speech tagging. So you assign a part of speech label on each word, okay? So, and then this is a joint task, You need to first chunk and then assign part of speech labels. So this is, you combine two tasks together, okay? A joint structure, okay? I love natural language processing, okay? So there are pronouns, there are verbs, there are nouns, they form a sentence. You have to recognize the word and then label them. Similarly, you can have a joint part of speech tagging and dependency parsing task where you first assign a part of speech to each word in a sentence, and then you build a dependency tree on top of the words. Okay, complex output spaces. All right. So the third type of the task is called a generation task. Okay. So I showed you examples last week. So there are a text summarization, for example, right? The input is a long text, the output is a shorter text, but you have to generate the output token by token. So this is a generation task. Machine translation is another one. The input is one language, the output is another. Okay. Code generation is another one. The input is, well, the specification of the functionality, and the output is the code. Okay. Input, output, generation task. For generation, there's a more general scenario, which is a generic generation model, large language model, for example. Okay. For machine translation and text summarization, the input is here, the output is a fixed functionality, right? For large language models, it's generic in the sense that you give it an input, but you also give it a specification of the task. Okay, one model can do a lot of different things, all right? So, for example, it's a large language model. You specify, please generate a poem for me. Okay, the poem needs to contain this word, that word, that word, and the output is a poem. But this kind of a model can also say, okay, let's prove a mathematical theorem. Okay, it's not a single theorem prover, right? So it's a generic model, so you tell it to do anything. So prove a Bayes theorem. You will review the theorem later today. Okay. And of course, it can also perform general tasks such as machine translation, summarization, and code generation. Just tell the model what to do in the instruction, and it will do it. Okay, this is generic generation task. All right. Just to recap, over this semester, I will tell you models to do these 3 types of tasks, okay? Maybe I will not spend a lot of time on one specific task, okay? But I will spend time on how to build a model for one type of task, okay? So I also hinted on this like last week, right? And you will see that these tasks have something in common, which is the output or part of the output is discrete in the sense that it's just one label or one token. It's not a continuous number, right? Okay. So for these kind of tasks, okay, we will learn the nature of the tasks. So as I mentioned to you, in that picture, there's data, there's model, right? If the tasks are like this, how do we build model? So there are some common thinkings when building a model. So remember this picture, the input is here, the model is here, the output is there, all right? So the first question I want to ask you is, how do you generate the output, okay, given an input? Okay. Well, if the question is to tell you, okay, what is 3 plus 5, right? So it's easy. You build a neural network, the output neuron is a number. Okay, you try to make the neuron fit the number, that's calculation. But for us, it's a little bit different in the sense that the output is discrete, right? We want to find a label out of a set of labels, right? Or a tree out of all possible trees, or a sentence. How do you do that? So the difference is that, okay, we could build a model to score all different kinds of outputs, okay? So you know the neural networks or the whatever models, and they will calculate the score given an input x, given an output y, okay? I will just score, okay, how good is y, okay, given x. And this model will have a set of parameters or the numbers we can change in a model, such as neurons, connections in neural networks, okay? I call this set of parameters theta, okay? So my basic thinking is, okay, for whatever task we have, I have an input and I have an output. I try to score the output given the input according to a set of model parameter theta, and that function can be called fxy theta. All right, so and these are suitable for discrete outputs. Okay. So next, the first thing I want to say is, well, for probabilistic models, a lot of models we'll learn are probabilistic models. Okay. This function fxy theta will be the probability of y given x using theta. Okay, it's a probability model. So you use the model to calculate the probability of y given x. All right. Also, I said you want to calculate the score of a sentence, which could be done by calculating the score of every word individually. So you break the whole problem of a complex structure or generation into sub-problems, okay? When you have the sub-problem, you could take the same thinking, okay? All right, we will see models that are built by treating a subtask, one token, as y, not the whole sentence as y, okay? So in this example, I said, if I want to generate a sentence, I ate pizza with a fork, okay? I break the problem into the prediction of one word after another, okay? So that every y is a word, right? So the x could be, I have generated, I ate a pizza with. And the y will be the next word. This is called Next word, a prediction. Okay. And one more thing. So how do you specify that f? Okay. Well, for linear models, I draw you one equation. So this f x, y, theta could be defined as, I first find a representation of x and y. Okay. I turn x, y into a vector. Can I do that? Okay, I didn't tell you how to do that, but think about that, okay? So you try to map some linguistic structure into a mathematical form, okay? A vector. The vector will represent the characteristics of these x and y, okay? And then my model parameter is another vector called parameter vector. I just use the dot product between this representation vector and the model parameter vector to calculate the score. Okay? And you know this is a linear function, and I call this kind of model a linear model. Okay, just to give you an example, right? How you can calculate fxy. But you can do another thing, which is, well, if I have a big neural network, what can I do? Okay, so maybe I first turn x into a vector, right? And then I feed this x into a neural network, and then the neural network will score all possible y. That's also a possibility, right? So you define another scoring function. So whatever you define, okay, the process of defining a scoring function is called parameterization. Okay? You find a set of model parameters and you find an equation to score a y given an x. Okay? So this process is called parameterization. All right? So from next week onwards, we will gradually learn different ways to parameterize a model, okay, to score some outputs. Now, if you are given a model, how do you get the output? Okay. Now you can score outputs. Then the problem becomes easier. So you just need to enumerate all possible outputs, okay, and score each of them. And then you try to find the highest scored output, and that's your output. That's your model output. Okay? So for example, if you're given, I love natural language processing, okay? You want to decide whether it's positive or negative. What can you do? You score, okay, this input with positive output. Score, 95. Now you score this sentence with a negative output, score 5. Say, okay, and then the first one is higher scored, so I choose positive as the output. Okay? So that's the basic thinking. And then, you know, for structured tasks, this can be non-trivial. Because how can you enumerate all possible trees and score each tree? When you learn algebra, you learn asymptotic complexity, right? Yeah. O(n) squared, right? If something goes beyond polynomial, it's called intractable, right? So if you count trees, they are typically intractable. All right? So you need some clever algorithms to be able to find the highest score tree, okay, for structured prediction. And that's what we will also discuss. But that's the general framework, okay? Bear this in mind when we move on to next week onwards. Now let's talk about training. So that's what the second picture shows, okay? So you have some data, and you want to distill the knowledge of the data into your model, right? So the model are model parameters. So basically, you want to specify what is fx, y, theta by filling theta using the data. So there are several paradigms you can use. The first is the data contains XY pairs. Okay? Document, label. Document, label, a lot of such things. And then you can train the model by learning from these Y labels, right? For example, you ask humans to label the Y's, right, given a lot of X. This is called supervised learning. It's like the teacher has the answer, and it tells the model, okay? So this is called supervised learning. I guess most of you know it, right? She's in a machine learning class, right? And the second is unsupervised learning. So the task is to transform X into Y, but well, what we have is only X, okay? So how can you transform X into Y without knowing how people label Y? So this is called unsupervised learning. Unfortunately, I will not teach you unsupervised learning, but the textbook has it, okay? You can read for the first edition, chapter 6, chapter 12, like chapter 7, chapter 18, a lot of chapters, they will contain such elements. I will not tell you about them because the term is only these 16 weeks. Of course, there is semi-supervised learning, SSL, which is, okay, you have some data with X only and some data with X and Y, and you want to train a model that maps X into Y, okay? Semi-supervised learning. But there is something I am going to tell you, which is called self-supervised learning. It's used a lot in pre-training, okay? So self-supervised learning is like, we don't have a task to specify. All we have is the data itself, okay, like text. And all the task we want to do is just to reproduce the data itself, just to reproduce the text, okay? For example, we want to recite things over the internet, okay? By doing the next token prediction, as I just showed you earlier, right? So if you have a lot of documents over the internet, and you try to ask the model, okay, if the previous words are these, what is the next word? This is called next word prediction, okay? So the input and output are both, okay, from the raw data. So you don't have a task. So this is called self-supervised learning. All right? So, so it's supervised learning, basically. And there is something I want to mention to you that that is the scale of the data is important, okay? So when you have more data, you might get better models, okay? So what does this mean? This is like the x-axis is the size of your data. The y-axis is the loss or the errors a model make on training data, okay? Then you'll see as the data grows, the model becomes more accurate on your training data. The loss becomes smaller, okay? And the model size also matters. You find that for larger models, okay, the loss can go smaller, right? But for smaller models, as the data size grows to the same level, the accuracy doesn't necessarily fall down. So scaling is important. I mentioned the scaling law. This is the second time I mentioned scaling. More data you have, the the better model you could have, right? There is a lot of engineering. Okay, I will mention that again later. All right. So this is the trend, right? This is the trend. All the trends are like this. All the trends are like this. No trend can be like this. If they are like this, then artificial superintelligence will come very soon. Okay. All right. So this is training. After you train a model, all right, you want to get an idea, okay, how good the model is, all right? So you have ChatGPT and you have DeepSeek. You want to know, okay, I want to use one of them. Which one shall I use? How do you choose it? Okay, there are a lot of benchmarks, right? Doing mathematical questions. And there are some scores on those benchmarks. You will see, okay, this model performs very well. I'll choose this model. So this is quantitative evaluation. Okay. And sometimes you don't do quantitative evaluation. You just try to get a feeling, right? This is qualitative evaluation. Let's talk about quantitative evaluation. It's also called empirical evaluation because this is evaluation based on data. Okay, benchmark. What is benchmark? So generally, you could have data as a set of labeled inputs and outputs. Okay, so you have a set of data, and each instance has a gold standard output. All right, and then how do you measure the model accuracy, the model performance? You use the model to make a prediction on every test input. Okay, you get the test output, right? I call that Y prime, right? So you have a set of test data, and on each test instance, you have a gold standard output, you have a model output, right? And what do? You compare them, right? You compare them. And then you calculate a score. That score tells you how good the model performs, all right? So this is empirical evaluation. But there are many things we need to be aware of under this dome. Okay, so maybe the first thing I need to say is the more test data you have, right, the more reliable the result is in general. But how do you know that it's already reliable? I will tell you later, called significance test. Okay. The second is, well, I just told you how to compare, right? You need to calculate the score by comparing Y and Y prime. How do you do that? That's called evaluation metric. Evaluation metric. There's a very simple one everyone knows. Okay, let's say for classification, right? Suppose that you have 1,000 test samples, right? And your classifier did 900 correctly. You calculate the accuracy as 900 over 1,000, okay, for classification, right? That's very simple. But we could have more complicated scenarios. Let's say I want to look deeper into the specific classes, okay? Now suppose I'm doing sentiment classification and there are 3 class labels, the positive, the negative, and the neutral, all right? So you want to look at the positive class. Suppose out of your 1,000 test samples, okay, 500 of them are positive, okay? In your gold labels, right, 500 are positive. And then your model made predictions. 600 of them are positive, all right? And out of these 600, 440 are correct. Okay, so this is the scenario. Let's just look at the positive sentiment. And you got this picture, right? You got this picture. So according to the data, there are 500 positive instances. Okay? According to the model, there are 600. And 440 of them are matched. Okay? But there are like 60 of them that are, according to data, it's positive, but according to model, it's either negative or neutral, right? There are 160, according to the model, it's like, according to the model, it's positive. But in the data set, it's either negative or neutral. So I can't just have a one metric to describe this phenomenon. All right? So I need to set out two metrics to describe it. All right. So one is, okay, let's think about the data, right? So I have 500 instances, and 440 are correct. Okay? So which means the model found, okay, 440 out of my 500. Okay, this is called recall from the data perspective. You use the correct one to divide what the data has, so this is called recall. Okay. So if you take another perspective, it's model. Okay, now I have a model. I predicted 600 positive classes, out of which 440 are correct. Okay, so how precise is my model? I use 440 to divide 600. So this is called precision. Okay. All right. So you have two perspectives. So I say, oh, if I want a metric to unify precision and recall, what can I do? Okay. So you can have a balanced score called F score. So the F score can give a ratio. So like, how do you weigh recall over precision? Typically, for a lot of tasks, if you want to just take a balanced measure, you use 1. Okay, this one means you pay the same attention to recall and precision. And the calculation is 2 times precision times recall divided by precision plus recall. Okay, so if they're the same, you get the number. If they're not the same, it's a compromise. Okay. Why do you care about precision and recall? Because sometimes you really want to detect a certain label. Let's say, for example, spam filtering. Okay. There are 2 classes. So one is the email is spam. The other is it's not a spam, right? What you want is, I want to filter all the spams, right? But I don't want to filter my normal emails, right? So, so let's if I take the spam perspective, right? What do I want? I want the recall or precision. If I take the recall, it means that, okay, I get all my spams in my spam detector. Then typically you sacrifice precision, which means from all those that are decided spam, there are good emails. Okay. But if you favor precision, it means that some spam emails will come into your inbox folder. All right, so this is a trade-off. Now still, let's think about sentiment classification. You have precision and recall for positive, negative, and also neutral labels. Now you want to get an overall score, right? Overall score, just like accuracy. So how does my model perform like generally? So, and that you can calculate the F score for positive, negative, and neutral. You have 3 F-scores. If you average them, it's called macro F1. Okay? And that one score can represent how good your model is in general. Okay? The macro F1 will treat every label equally, no matter how many instances they have, right? So for example, neutral sentiment can be very few, only 100 of them. A positive and negative can be many. But when you calculate the average, you treat everyone equally, right? All right. No matter how many citizens they have. All right. You just average them according to the label. So it's fair to every label. But in contrast, when you calculate accuracy, it's fair to every instance, right? Because accuracy is like for every instance, am I correct? Yeah, so they're different. So we have discussed several metrics. So we discussed the accuracy, the precision, the recall, F measure, and macro F1. So there will be a lot of different other metrics, okay? So for different tasks, we might use different metrics. And I will show you a few of them later when I discuss annotation. So, but this mechanic matching is not necessarily the only means of evaluation metric. So sometimes when the problem is very abstract, we might want to use a model to help us evaluate. For example, in machine translation, okay, it turns out that some of the mechanical matching metrics are not very faithful, or they do not align very well with human annotation. As a result, you might ask another model, okay, such as a large language model, to evaluate the results. Okay, so what perspective do you want to pay attention to when you do such evaluation? For machine translation, people typically care about 2 mainstream metrics, such as the fluency and the adequacy. So the adequacy is basically to say how faithful, right, is the translation to the original sentence or passage in terms of the meaning. Okay, and the fluency is to show how grammatically correct and fluent is the output. All right. In addition to those, there are of course other metrics you can define. For example, how well does the output fit culturally to the native language, for example. So you can define a lot of metrics. And with every metric, you just ask a large language model, okay, try to score this thing from 1 to 5, for example. Just like you're trying to ask a human annotator. Okay. So, model-based evaluation, there are also other scenarios. For example, I should say there are also different scenarios. For example, you can have a reference-based evaluation. So basically, you have an X. For example, I ate it yesterday. And you have a gold standard Y. Okay? 我昨天把它吃了. Okay? And then you have a model output, Y prime. Okay? 昨天我吃了它. All right? And then the evaluator's task is to compare this model output with the reference to score whether it's adequate or fluent. Right, this is reference-based evaluation. But you could also have reference-free evaluation, which is more demanding on the model itself, right? On the knowledge from the model itself. It says, I only tell you that the input is I ate it yesterday. And the model output Y prime, okay? Now you tell me, okay, how good the translation is. It requires that the evaluator model must have knowledge of machine translation. All right, so this is called reference-free evaluation. But how do I know that the model score is reliable? Okay, so if the model gives us a score of 4.3 out of 5, can I trust it? So generally, you could have humans to evaluate the quality of model evaluation. And this is called meta-evaluation, evaluating the evaluator. Okay, this is called meta-evaluation. Of course, human evaluation can be the most trustworthy, all right? But human evaluation is costly, so it can mostly be done in a small scale. All right, so we talked about how to match an output y prime with a reference y, how to evaluate using mechanic metrics or model-based evaluation metrics. Now suppose you have a set of test data, okay? And over the set of test data, you have two models. Model A is scored 93%, and model B is scored 95%, okay? The question I ask you is model B necessarily better than model A? So apparently, if you look at the test score, right, model B is better by 5%. But all I care about is this score generally true? So in some unseen data, okay, does model B still score higher than model A? So I guess this is a question we want to ask, right? It's also the same as your exam, right? So student A scores better than student B. Does it reflect that student A is really better? As I mentioned to you earlier, so the larger the test set, the more reliable the score is, right? But that's only an intuition. So to quantitatively know the difference, okay, there's a statistical measure called significance test. What does it do? So basically, you have a null hypothesis, which is to say, maybe the two models are not essentially different, okay? So model A only scored worse than model B by chance, all right? So this is the null hypothesis. And according to your test data, okay, you can calculate the probability of this null hypothesis, okay? So in other words, you calculate the probability that model B is not really better than model A, but the performance is only by chance better, okay? Of course, the lower this probability is, the more trustworthy your result is, right? Okay? So there are different probability levels. For example, one level could be 0.05. Okay, there's only 5% chance that the null hypothesis is true. Okay? Or another level is 0.01 or even 0.001. So this, we call it significance level or P level. Okay? So when you report, when you try to obtain, okay, some results, in addition to the absolute performance, when you compare different models, you can do the significance test. Okay? There is a common significance test called the t-test. Okay? All right. So all of the significance tests give you a metric, give you a measure on the significance level. The lower it is, the more reliable it is. And of course, the larger your test data is, typically your significance level is lower. Okay, so your result is significant. Okay, you say my result is significant at the p-level of 0.01, for example. Okay, normally you report your result in this way. So if the significance level is 0.01, it means that it's very trustworthy. Okay, even if it's even smaller, then it's more trustworthy. Okay. Concerning evaluation, there's one more thing we need to talk about, which is development test. So why is this important? Okay, so this comes from a fact that you sometimes need to tweak your model, okay, and improve it. In your project, I think you will do that. So you have a problem, you have a test set, and you build a model, and you know the test result. Okay, the accuracy is 5%. Okay, you say, no, this is a bad model. I want to make it more accurate. So you tweak your model, and you recalculate the accuracy. Great, now it's 90%. Okay, it works. And I want to make it even better. And you tweak your model again, and you measure, okay, 91%. And you further try to improve it. So this kind of repetitive evaluation should not be done on your test set. The reason is very simple, because one set of test data doesn't necessarily reflect an unseen set of test data. Okay? Any test set has its own peculiarities. Okay, unless it's huge, it's right. So if you tweak your model to maximize its performance on your test data, you have a risk of actually tuning the model to fit the test data too well, you know, and then in a set of unseen data, it will not perform very well. I mean, it might be even worse than your original model. You want to avoid this situation. Okay? So, in order to avoid that situation, you need to prepare another set of test data. And that data is called development test data or validation data. Okay? So you want to tweak your model repeatedly on your validation data. Okay? And then when you see that the model performs very well on the validation data, and you test it on the test data. If it performs badly, it means that there is something wrong. Okay? It fits the development data too well. Okay? So this is the general scenario normally in your model development. Okay. But then you say, okay, my labeled data is too small. I mean, maybe I only have 1,000 labeled data. I can't just afford to split it into a training set, into a reliable development set, and a reliable test set. Okay? Then you could also do a cross-validation to develop your model. So the basic idea is when your data is small, okay, you cut your data into k parts. Okay? When k is 5, it's called 5-fold cross-validation. When k is 10, it's called 10-fold cross-validation. Okay? And then you take turns to make each part the test data, and the other remaining parts combined together as the training data. Okay? For example, in experiment 1, you train the data using the combination of the split 2 to split k, and you test your performance on split 1. And in the second run, you train your model on like D1, D3 until DK, and test it on D2. Okay? So in the case fold, you train your like a model using D1 to DK minus 1 and test it on DK. Then you get K results. You average them together for the validation results. Okay? Because every time you randomly split your data into K different parts, you can also avoid the issue of developing your model too much on one set of data. All right. So I think that's everything I have time to show you for like the model and data part, okay? Including the tasks, the paradigm, the training, and the evaluation. Now, let's spend a few moments on data. Okay. Data sets are very important to natural language processing. So for the remaining of the term, we will be looking at how to build a model, right? We will not spend a lot of time on how to curate data. So I will spend some time today to this end. So normally, when you do something on data sets, in your labs, okay, you will have data sets provided for the few labs you have. But in your course project, you might end up collecting your own data. Who knows? Okay, depending on your project proposal. So if you need to label your data, or if you need to curate your own data set, so this is the rough procedure you need to follow. So first, you have to collect some data set, okay? So either by crawling the internet or by downloading some mature data set, okay? And then you need to prepare your data. You might use a large language model to label your data set, or you might label it on your own, okay? Or you might hire some classmates to label it. All right. And then after you label the data set, you want to evaluate the quality of your data set, okay? Are they good enough to be used to train a model? And after you evaluate your data set, you might go back, okay, to relabel your data set, to change, to tweak your data set. Okay, it's very important. So when you train large language models, the data set plays a very important role. If the data set is of low quality, your large language model might not work at all. Okay. So first, about data collection. You need to know the domain of your data. So by domain, I mean you want your model to work very well on news, or your model is designed for solving social media data. Okay. And what languages does the data cover? Okay. Is it designed for the biological domain or code? Okay. Or it's a mixture of different domains. Okay. Or it's a mixture of different languages. If it's a mixture of different languages, what proportion of each language it should have, okay? So this will decide the performance of the data on the input data. Normally, if you train your model with a lot of English data, it'll perform very well on English, but maybe not as well on other languages, okay? So this is the first thing to consider. Second, okay, the data sources. Well, before you try to make your own data set, you need to first check whether the type of data is already available over the internet. For example, there are a lot of data sources out there already for training a language model. Okay, so for example, there is a book corpus, and there are like a corpus called C4. There are also other Wikipedia sources, which are a large data sets from the internet, which you can use to train a language model. And they are raw data from all different kinds of domains. There are also labeled data, okay? So, for example, when you do parsing task, there's a pantry bank. You can directly use the data. And if you purchase a license, right? And in addition to this kind of manually labeled data, there are also something called silver data. What is silver data? They are data that has inputs and outputs, but the outputs are labeled by models. Okay, so people use a model to label the output for you. So these are called silver data. Okay, and you say, silver data are not as good as gold data. It depends. Human labels are not always reliable. This is something you need to know. For example, for part of speech tagging, right? You get data from the pantry bank. And people have shown you that a linguist and another linguist, okay, agree at the maximum of 97%. Okay? So it means that if your model performance is 97%, then it's already at the human level. If it's more than 97%, you won't trust it, okay? Because humans only agree at 97%. So, after you check the web and you find that, okay, there's no relevant data you can use, what can you do? Okay, you must label it yourself, okay? By either using a large language model or by the human. So, you could crawl the data you need first. So in this part, you need to first build a web crawler. There are different resources you can use, like Python packages you can use to crawl the internet. Okay. Now after you crawl the data, you will find that some of them are not meaningful. They're not even sentences. They are random sequences of strings, right? You want to filter them or filter low quality data. And then you need to do some pre-processing. For example, you want to maybe, depending on your task, right? So normalize URLs into a same token, or normalize numbers, or do the capitalization, or do tokenization, whatever. So you do some pre-processing. And then you can consider labeling your data, okay? But whatever, no matter whether it's publicly available data or it's a private, crawled data source, you must first check the license. There are a lot of different licenses, okay? Some allow you to change it and publish it again. Some allow you to train a model on it, okay? Some allow you to do everything on it, but you need to pay attention. For example, if you want to collect some data on novels, which some of my PhD students did recently, then you need to check the license of the novel, okay? Is it already in the public domain, or is it still intellectual property? Okay. All right. So here I give you one example maybe. So there is a data set called WMT. So it's a benchmark for neural machine translation. Okay, you can download the data. But how do they collect the data? Okay, so first of all, they say, I want to download some training data and test data for machine translation. So how do I do it? Maybe I go to different sources, like United Nations data set or whatsoever, okay? And I collect documents in a lot of different languages, you know. So for example, Hong Kong, the government has bilingual data, right? The United Nations has multilingual data. You have these documents. After you collect such documents, okay, from different sources, so one thing you want to do is you want to check the quality, okay? So nowadays, a lot of multilingual data on the internet are actually translated by machine. Others are translated by human. So if you collect a lot of data that are translated by machine and you train a model, the model will cause translation needs phenomenon. What it is? So it reads like machine translated data. Okay, it's not that natural. So you want to filter our data to ensure the data quality. And then you need to do some pre-processing because the document corresponds to the document, okay, English, Chinese, okay. But they're not aligned sentence to sentence. You want to train a machine translation model that translates by the sentence. So what can you do? You need to cut the document into sentences and align the sentences, etc. Right? And then in the end, you got a corpus. Okay. So this is how do you crawl some data and pre-process some data. And then, so how do you evaluate machine translation? I mentioned to you, so for one data set that you release, right? In addition to the training and test data, you also want to release the evaluation metric so that people can use your benchmark. So there are some like mechanical evaluation metrics. One is called the blur. One is called the commit. One is mechanic, one is model-based. So how does blur work? Okay, so this blur, okay, it matches the reference translation and your output translation by words and phrases you can think about. Okay, so how precise the precision of small text bands in your output, are they correct? Are they correct? So you have this measure and you have a length penalty, and after all, you can match output to a reference and assemble a score. Okay. So commit, on the other hand, is sort of a model-based evaluation metric. You just use a model to give scores on some metrics. All right. So now let's move on to annotation. I have to flip through them because of time constraints. But when you do annotation, okay, you can read the materials offline, okay, if you need. All right. So, but basically, this is a time-consuming process, and it's an iterative process, as I showed you. You need to develop some guidelines, okay, to show the human labelers how do you label this data, right? And sometimes you need to develop or download some annotation tools, okay? So for some problems, we develop like interfaces for humans to collaborate in annotating the data, okay? And then after you have the tools, you have the guidelines, you do some round of annotation. So ask every annotator to maybe label 50 sentences, 50 inputs. And then you check the quality. I will show you some metrics to check annotation quality, okay? And if the quality is very bad, sometimes it is, okay? Then you need to go back to revise your annotation guideline. Is it too fine-grained that people cannot agree with each other, okay? Is it not clear enough or something? You adjust your annotation guideline and you do the pre-annotation again, okay? Until you find that, okay, the quality is great, everyone can agree, right? And then you do the formal annotation in large scales. You hire some like annotators, you hire some verifiers to do the annotation. After you get the data set, you use the data set to train your model. And even at this stage, you might find, okay, the data quality is low, okay? The data quality is low. So in this case, you might even need to go back and revise your annotation guideline and revise your annotations. It's an iterative process, okay? So, in your annotation guideline, you need to specify, okay, what's the goal of my annotation? Okay, what do I want to annotate? And then the annotation schema is like, how do I label? So you need to first specify, okay, what are the labels and where to put them? And you need to give the annotator some examples. Okay, how do you label the data? And you need to tell the annotators the annotation process and tools they use, of course. So this whole document is what you need to assemble and like distribute to the annotators before they make annotation. Let's take a very simple example. So suppose you want to classify news document, okay, into political, technological, financial, and sports categories, 4 categories, all right? Then you need to tell the annotators, okay, the goal is to label for news classification, and these are the label sets. And then you need to say, the format is you're given a document. Now, you make the first line of the document empty and you put a label to it. For political news, you put P on the first row. For technological news, you put T in the first row, etc. Okay? And you give an example on the right. Okay? And after they read it, they think they can annotate it, you go around the pre-annotation. So you ask 2 labelers to label 50 news documents, okay? And then you match, you try to check, okay, whether they agree with each other. If they mostly agree, you can go on to label more, okay? But if you don't, you go to modify your specification. Okay, so for sentiment analysis, similarly, you can specify. The goal is to label for sentiment, and a data set can have either positive, negative, or neutral, or 1 to 5 star ratings or whatsoever. You specify that, okay? And then you give it a few examples. And after you release the data set, you tell the reader, okay, how to evaluate your model. Okay, for example, you can say you use accuracy and F1 measure, okay, to evaluate the model. All right. So this is for linguistic annotation. Suppose you're interested in syntax, okay? You want to do parsing, constituent parsing. And there is a data set called Pantry Bank, which is a good example. It contains about 40,000 sentences annotated with syntactic trees. And the annotator agreement is quite high. Okay? So, but for this task, you need to specify a lot of linguistic knowledge. I just show you here as an example. The goal is to, annotate constituent trees in hierarchical phrase structure, and the label set include part of speech label set and constituent label sets, etc. Okay, and then here they list the whole set of parts of speech. Okay, NN means noun, NNS means plural noun, etc. Okay, a whole set. All right. And then there is a very long document about how to annotate these syntax structures. Okay. It's a PDF file which you can download from their website. Very long. And experienced linguist can read and annotate, and which they did. And then the annotation scheme is like you put brackets, okay, on embedded format to represent the syntactic structure. Okay, so each indentation level shows you a level in a hierarchical tree. And then they specify the evaluation metric, such as you calculate the F measure, okay, of the constituent spans. What is a constituent span? You can think about it as a subtree. For example, a verb phrase, like from the second word to the third word, a subtree. Okay, it's a span level. All right, so this is like the pen tree bank annotation. There are also other schemas. I leave the details to you to read. For example, there is a dependency tree bank called universal dependencies, and they specify how to label the noun entities and different kinds of different categories of dependencies between them. And they show examples of the labeling and also how to evaluate. Okay. There is also for relation extraction, for event extraction, for natural language inference, question answering, etc. There are different data sets with their annotation guidelines, which you can refer to when you try to build your own guideline. So finally, okay, quality control. So how do you know that your annotation guideline is great and your labeled document is of high quality? Normally, you do that by calculating inter-annotator agreement, which means when you have two people, okay, to label the same thing, how similar they are. This is called inter-annotator agreement. Typically, if your labeling is great, you can't afford to hire two people to label like thousands of documents. What do? You hire two people to label maybe 50 to 300 documents, and you can calculate an agreement score on this sample set. This is called inter-annotator agreement score. There are different metrics to calculate the agreement, and I here introduce one to you called Cohen's kappa. It's a kappa value. The value is calculated in this equation I will explain to you later, okay? It's P0 minus PE divided by 1 minus PE, where P0 is the empirical agreement. You calculate the agreement. And PE is the expected agreement by chance. So in theory, okay, how likely they agree, okay? So the basic idea is if they actually agree a lot, right? And the chance that they agree is not that much, okay? So this ratio over 1 minus the chance that they agree is big, then they agree a lot, okay? So this value is between -1 and 1. So if the value is greater than 0.4, you think that, okay, these annotators, they agree very much. And if it's above 0.6, you think they strongly agree with each other. So here I give you one example. So again, let's take sentiment classification, for example. If you have like 1,000 documents, okay? And annotator A labeled 500 as positive, 400 as negative, 100 as neutral. Annotator B labeled 450 as positive, 460 as negative, and 90 as neutral. Okay, these are two. And then how much do they overlap? For positive one, they overlap by 400. For negative, by 380. For neutral, by 80. Okay. So for model evaluation, you had a case. So now I think it's easy for you to understand the scenario. So if you take the positive one out, for example, so A has 500, B has 450, right? Their overlap is 400. So it's this scenario. So how do I calculate P0? P0 is how much they actually agree, right? How much they actually agree. So when I calculate the ratio for their agreement to A, you just calculate the 400 over all the samples. You get a ratio. And you calculate the agreement, you calculate their agreement for positive, for the positive label. It's like 400 they agree over all the data set, right? And you can also calculate the ratio for a negative sample and neutral sample. You add them together, it's a ratio, right? Okay, it's the ratio of all the instances where they agree. So this is P0. All right. So what's the probability that they agree by chance? Okay. So you can calculate basically the probability that annotator A will predict any document as positive. How do you do that? That's 500, right, divided by 1,000. So if annotator A annotate any document, the chance of A annotating it as positive is a half, right? You can also calculate that for B, positive for B. Like out of the 1,000, B annotates 450 as positive, right? So given any document, by chance, B should have 0.45 as positive. All right, so now, given any document, what's the chance both A and B labels it positive? According to probability knowledge, you just multiply the two numbers together, right? Okay. It's 0.5 times 0.45 is 0.225. Okay, so this is, okay, by any chance, two labelers both label something as positive. Okay, so this is PE for positive, and you can calculate the same for negative and neutral, and then you can calculate an overall PE. All right, by adding the numbers together, and then you can try to calculate the kappa between the two annotators from the equation I showed you in the last slide, and in the end it's 0.76. Okay, it's very high. It shows you that, okay, your data quality is great. Right. I have to stop here due to time limitation, but I think I have time to fit this review of probability theory next week.